All right, and I see that we're live. Welcome everyone to the afternoon concurrent session of the ninth Annual University of Maryland Symposium on Environmental Justice and Health Disparities, hosted by Dr. Shakobi Wilson at the Center for Community Engagement, Environmental Justice, and Health. I'll be the moderator for this session. My name is Vivek Ravichandran, and I'm a PhD candidate at the University of Maryland, and I've worked under the supervision of Dr. Shakobi Wilson. And this session is entitled Unmasking Environmental Injustice, How Low-Cost Sensors, Weather, and Satellite Data Are Revealing the True Cost of Pollution. So I'm just going to go ahead and introduce our esteemed speakers in the order of which they'll be presented. First up, we have Dr. Eben Cross. Dr. Cross is the co-founder of QuantAQ, where he and his team have combined distributed sensor networks with strong fundamentals in atmospheric chemistry, data science, and software engineering. We're also joined by Ms. Teresa Espy. Ms. Espy is the Chief Operations Officer for Diamond Scientific, which is a small veteran-owned authorized distributor and service provider of gas monitoring equipment in Cocoa, Florida. Moving on to our academics, we are joined by Dr. Susan Annenberg. Dr. Annenberg is the chair of the Environmental and Occupational Health Department at the George Washington University Milken Institute School of Public Health. She's also the director of the George Washington Climate and Health Institute. Dr. Annenberg's research focuses on the health implications of air pollution and climate change from both local to global scales. She's also served on various federal government and international advisory groups and work groups, and I hope she'll be able to bring some of these memberships during her slides because it's a lot to cover due to her esteemed membership statuses. And last but certainly not least, we are joined by Dr. Sally Pasude. She is the associate professor in the Department of Environmental Sciences at the University of Virginia, and her research group focuses on advancing the application of satellite remote sensing for describing, understanding, and informing decision-making around air pollution environmental justice issues. Additionally, she's the co-director of the Repair Lab, which is an interdisciplinary EJ laboratory at the University of Virginia. So without further ado, let's jump right into our presentation series. And we can start with Dr. Cross. So if you'd like, you can go ahead and share your screen with your presentation. Thank you.
Great. Can you all see my slides? Sorry, I've lost my visual of you if you're nodding your heads.
Yes, we see it.
Okay. Great. Well, thank you so much for the invitation. I really appreciate all of the work that UMD has put into this over the years. This is the first time that I've been participating in this conference, and I'm really, I'm blown away by the ability to organize such a thing. So really appreciate the opportunity. I was going to hopefully use my time to sort of focus on this concept of building an air quality community of practice. And through that, how to enhance and empower sort of local air quality capacity. My name is Eben, and I'm the Chief Science Officer and co-founder of a company called QuantAQ. And we've been working on building distributed sensing solutions for community for the better part of the last 4.5 years. So as a sort of an example or a lesson that I've learned from my second grader, I should begin with the end in mind. And so I'd like you guys to take away from today's session, what do I mean by air quality community of practice? What does it really mean? What are the ingredients? How have I seen it sort of fail, and how have I seen it work well? And what can we do from here moving forward? I'd also like everyone to understand that we are sort of living in a paradigm shift where local air quality monitoring is becoming a thing that is immensely valuable and potentially useful to many, many different stakeholders. I'd also like folks to understand that data alone is unhelpful and insufficient, and that we have to figure out ways to convert data to information in order to actually have impact. And part of that story is really understanding your sensor's blind spots. There's no such thing as a perfect sensor, and understanding what makes these things imperfect can be quite useful in terms of avoiding frustrations. And lastly, I'd like to just highlight some of the communities of practice that are in action, some of which are shown here, spanning locomotive electrification efforts in Boston, industrial agriculture impacts in the Delmarva Peninsula, and sort of metropolitan sort of houses of worship based networks that are emerging in St. Louis, just to name a few. So when I think about how do we solve the local air quality capacity gap, I really see three ingredients that need to come together for these projects to be successful. And the parts of this triangle have not traditionally always worked exceptionally well together. But I think moving forward, if we are going to have impact, we really need to ensure that we can build communities of practice that involve all three of these players. That's a government player, that could be a city, a municipality, a regulator on the one hand, researchers who have been in the space and know all these nitty-gritty details about air pollution and technology solutions, but also community. And the community brings a layer of expertise that I think traditionally has not been respected on a level set with these other entities. In other words, we end up in situations where we often cloud over the top part of this triangle, and we have a lot of interactivity between government players and researchers and government players. And that's not helpful. It doesn't drive lasting impact. It doesn't build local air quality capacity. In the same way, I think there's a pendulum swinging back towards community. And in a lot of cases, we end up seeing situations where the community is sort of left on their own to figure it all out. And we also need to avoid this situation. So ideally, we end up in a situation where together these groups can clearly identify the question that needs to be answered. They can own each of their strengths and weaknesses. And the weaknesses part there is really important because that's about sort of checking egos and understanding the things that you don't do well as the things that you do well. And then aligning incentives between the groups and sharing a definition of success. And if we can do this, we can actually achieve some pretty remarkable things, in my opinion. So the paradigm shift that we're sort of up against right now is a shift from regional air quality to local air quality. And this is profound because the way that we've built monitoring infrastructure in the United States is to serve a regional purpose. And by design, that network is intentionally avoiding local air pollution hotspots. And people don't know that, but that is the way that has been built. So from a regulatory perspective, there's a bit of a mismatch between local air quality problems and regional air quality monitoring infrastructure. And you can see this, there's about 1 million people that live in this square around Boston. There's 4 triangles. Those are the regulatory monitoring sites for Metro Boston. But if we look at what happens in the city, we can see there are disproportionate sources of air pollution everywhere you look. And none of those impacts are being captured or characterized adequately by the regional monitoring infrastructure. So this is, when I say paradigm shift, I mean, we want to be able to make measurements where pollution is occurring, but we also need to be able to make those measurements in many, many more places at higher temporal resolution than the regional regulatory monitoring network has ever done. And that's the shift. The granularity of information and the relevance of information is much, much higher when we go from regional to local. The forcing function here has a lot to do with this spectrum of cost and the spectrum of scale. And so what I'm doing here is I've just shown that we can move from $10 sensors on the marketplace on the one side to situations that are highly specialized and hundreds of thousands of dollars worth of kit on the other side. And if we land in the middle, we can sort of hit this sweet spot where the technology can be robust enough, it can provide data quality that's sort of a known data quality objective, and we can begin to use that technology at scale without sacrificing a whole bunch of overhead and complexity that comes with higher fidelity instruments that are deployed in the regulatory monitoring network. So we really want to target this sort of $1,000 price point object that we can scale into communities and provide robust air quality data and information. From QuantAQ's perspective, we're scientists first and sort of sensor manufacturers second, and we're trying to build this local air quality infrastructure in a way that it can in fact scale. And this is quite different. than the traditional monitoring instruments. You have to have connectivity. Things have to be able to connect to the cellular network right away. You have to power it via solar. You have to be able to deploy it and leave it. And the data has to come out of it with some known calibrated quality function. That data also has to come out quite frequently. It has to be on a 1 minute base so that we can characterize the information on that local scale as it's changing over the course of an individual plume. And we have to be able to design the data management side in an accessible and shareable way. So this really sort of puts us in a position to do something that's quite different than the traditional regulatory monitoring network. We need to move beyond just get more air quality data, but we need to actually be able to deliver air quality information. So we need to convert that raw data to actual information. And this gets back to centering on questions that the community needs to be addressing and answering, and linking that to what the technology solutions can provide in terms of informed information. And this is just where all the cloud architecture that underlies robust products that we deploy in the field ultimately has to be pre-positioned to deliver that information in a way that's useful. Otherwise, things get really overwhelming and they don't add value. So I think at this point, we've touched a little bit on the community of practice, the paradigm shift. The data alone is insufficient. We really need to push towards information. How do we understand these blind spots? So I'm just going to talk about one example for the blind spots of sensors, and it's with respect to particulate matter. Now, what we've learned in low-cost particle sensors is there's two different flavors. One's called a nephelometer, and it's good at measuring basically the stuff that's below 1 micron in diameter in the atmosphere. The other's called an optical particle counter, and it's pretty good at measuring and differentiating particles of size between about 0.5 micron all the way up to 40. So if you have a situation where you have dust in the air, you can't rely on a nephelometer to make a reliable measurement of those particles. And some sources do generate a lot more dust than they do sort of combustion generated aerosol. On the off hand, like if you only have an optical particle counter, you can't see those smallest particles from those combustion sources. And so you need to rely on the nephelometer to tell part of that story. So there are limits to each one of these approaches. And from our perspective, you can build a stronger approach to making the measurement by combining these technologies into one box, which is what we've done with our technology. So we have both a nephelometer sensor and an optical particle counter together, sort of informing the full span of particles that occur in the atmosphere in these environments. So one example, and seeing this sort of used, is if we go to a place like Coachella Valley, there tends to be a lot of dust there, and we can end up comparing the response that we get from these sensors to the response that we get from regulatory instruments. Now, the trick here is we're trying to carve that channel where we have alignment between the regulator, who cares about the reference instrument, as well as the community, in this case, the tribal community, 29 Palms, who wants to inform the community about dust exposure. And so we can show over time that because of the combination of PM sensors used in this particular sensor box, we can match the response of that reference instrument without any modifications or interference from us. It just works out of box in a way that's consistent for a long extended period of time. And you can start to compare those outputs both from the lower cost device to the higher cost device, and you can see that they're telling a self-consistent story. And in fact, in some ways, we're exceeding the performance of the higher cost technology, which, by the way, has a babysitter every couple of weeks who has to take care of it. So the overhead is a thing that's managed a little bit more easily with the distributed sensing asset. The important thing about our technology is we also have the PM10 story that we get from that nephelometer sensor inside the box. And if we look at this data from the same exact time period, we can see that it catastrophically fails to measure the dust that happens to be in the air. And so this is a really important factor to consider as we sort of navigate the space of what are sensors good at, what are sensors bad at, which ones are which, and when do we need to basically think carefully about aligning the technology choices that inform network deployments as we build out air quality capacity on a local scale. So I don't want to take too much more time. We only have 3 more minutes, but Again, the community practice in action. Identify the question, combine the strengths of everybody on all three sides of this triangle, align incentives, and then sort of share that definition of success and aim for it. And in the last couple of minutes, I'll just walk through one example. This was a train electrification study run by Air Partners and Fairmont Indigo CDC Collaborative. So this is a community group pairing with a research team with ties to the policy ecosystem. And essentially what each one of these players did is they brought their strengths to the table and they shared the goal of wanting to help communities sort of understand and lower their exposure to air pollutants. And Air Partners does that through long-term policy maneuvers, as well as direct interventions, filtration interventions, as well as the community, which brings the goal of we want to build a healthy and thriving community that has affordable housing and access to affordable transportation. And throughout this part of Boston, we're using a diesel commuter line rail essentially as a subway. What this means is that we have diesel locomotive emissions that disproportionately impact subsets of this community. And these are high densely populated communities. So we can see that disproportionate impact if we were to have air quality evidence to layer on top of the use case of this diesel locomotive. And that's what was missing. They had introduced a bill, but they didn't have the evidence to support it. And that's what the team set out to do by combining the sort of research expertise of using sensors and higher fidelity kit. We could build out basically two outputs. We could build technical reports on the one side, which is the data reporting feature, and we could also work together with other stakeholders and experts to build out a web story and narrative that we could then use to build stakeholder and base building efforts, which then just substantiates the goal of sort of reaching the community in a deeper and more aligned way. So I'll just close by saying we really want to move data to information. We want to align the tech with the questions that are being asked, and we want to use this community of practice to sort of drive positive outcomes and impacts with our eyes up wide open to the challenges that come with that. And with that, I'll leave you with my email. You're welcome to reach me at evan.cross@quant-aq.com.
Thank you so much, Dr. Cross. And you mentioned these monitors that provide value at a fraction of the cost of some of these other government monitors. And I think that's a great theme to take away from this, as well as the community university industry partnerships, and of course, the EPA's series of community air monitoring grants. So thank you so much. And I'll save some of that discussion for the Q&A. But with that, we'll transition to Ms. Espy's presentation. So I'll just go ahead and share my screen so we can get that going.
Is it showing yet? There we are. All right. Hello, everybody. I'm Teresa Espy. I'm the COO of Diamond Scientific. We are an authorized distributor of air quality, landfill gas, and biogas monitoring instruments. And today I'm going to provide a short presentation on one of our air quality monitors, the S-Pod. Next slide. The S-Pod was developed to monitor air quality and provide data for the determination of volatile organic compounds in environments that are suspect for containing these pollutants. Areas like wastewater treatment plants often generate benzene, toluene, ethylbenzene, xylenes, tetrachloroethylene, and naphthalene. Landfills might contain vinyl chloride, and like wastewater treatment plants, they might generate benzene, ethylbenzene, and toluene. Coal-powered facilities used to generate electricity can generate particulate matter, nitrogen dioxide, and other pollutants. Next slide. Industries and environments that can benefit from the use of the S-Pod are oil and gas production facilities, municipal government services, i.e. utilities, transportation, local parks, etc. Industrial health, safety, and compliance, which include manufacturing facilities. environmental impact studies like near or at schools and wilderness areas, and emergency response, including hazardous spills and wildfires. Next slide. The method used by the SPOD to detect these pollutants is photoionization. The image at the top of the slide is a photoionization detector, also known as a PID. Inside of the PID is an ultraviolet lamp that excites certain gas molecules into positive and negative ions, which are then attracted to the negative and positive electrodes, thereby creating a current. The PID measures the charge of the ionized gas, meaning the greater the current, the greater the concentration of VOCs. Next slide. Here is a list of sensors that can be used with the SPOD. Not only can the SPOD use the PID, but it can be configured to accept a metal oxide semiconductor sensor, also known as an MOS, that can be used to detect carbon monoxide, carbon dioxide, methane, or non-VOCs like nitrogen dioxide and ozone. These compounds cannot be detected by a PID, but can using the MOS. An electrochemical sensor specifically for carbon monoxide can also be used with the SPOD. A detector for measuring particulate matter can be added in conjunction with the other sensors. Next slide, please. To aid in determining from where fugitive gases are originating, an anemometer can be configured with the SPOD to measure wind direction, wind velocity, temperature, relative humidity, and air pressure. Next slide. To access data in real time, the developers of the SPOD created SenseIt Connect, which is a cloud-based platform that allows the user to visualize a graphic along a timeline and includes not only detection of the VOC, but the weather data too. Next slide. While on SenseIt Connect, as I mentioned in the previous slide, the user can visualize the data in graphical form, change settings of the instrument, and download the data as a CSV file so that the user can then create custom graphics. Next slide. Additionally, while on SenseIt Connect, the instrument's location can be determined, thresholds can be set to obtain samples for later analysis. For example, a concentration threshold that exceeds a set amount of time can be set to trigger the opening of the canister to take a sample. Sampling can also be triggered for a given wind speed and direction range. The triggered sample will continue to collect for a programmed amount of time or according to pressure or volume. The valve then closes. An alarm can be set to notify the user via email or disconnected power or erratic readings. And of course, while on SenseIt Connect, fugitive gases can be detected in real time. Next slide. In the previous slide, I mentioned that a threshold can be set for the instrument to take samples. The SPOD can be connected to a valve controller, which is then connected to 1 or up to 4 sampling canisters. For example, on the SenseIt Connect platform, the user can enter a specific VOC concentration to actuate the valve on the canister. When the concentration in the air reaches the desired level, the valve controller talks to the valve to open the canister and take a sample. Next slide. Here is an example of fence line emission monitoring. The monitored site is a facility located near a waterway. Elevated VOC concentrations were observed through other methods. The SPOD was placed at the site and allowed to operate. To the south and southeast of the facility was a temporary barge slip. Data taken from the SPOD and downloaded to a graphical software confirmed that the emissions originated south and southeast of the SPOD. If you look at the circular graph, the SPOD is in the bullseye part of the graph. South is towards the bottom and north is at the top. The concentric rings represent wind velocity. Yellow is higher concentrations of VOCs, while dark purple or black are lower concentrations. And for additional confirmation, an optical gas imaging camera operating from a boat on the waterway provided evidence that the barges were the source of the VOCs. Next slide. This is a line graph representing wind direction and VOC concentrations during the monitoring of a refinery facility with adjacent industrial sites to the south of the facility. An SPOD was placed in the northwest corner of the facility. The blue line represents wind direction. On the left axis of the graph, the 0, which is at the bottom, represents north, and the 180 represents south. The 90 represents east, and 275 represents west. The 360 is north again, but the program defaults back to 0. The orange line represents the VOC concentration in parts per billion. The y-axis on the right denotes the concentration scale. Next slide. This is a picture of an elementary school, and in the background is an active oil and gas site. The Colorado Department of Public Health and Environment placed the SPOD alongside its mobile monitoring lab outside of the school. The mobile lab featured an impressive array of measurement technologies, but there was only one mobile unit in the department, and there were many potential sites requiring monitoring activity. The SPOD offered a low-cost and portable alternative. In this picture, you can see where one of the SPODs was set near the air monitoring mobile unit. In the mobile unit was a gas chromatograph, and installed in front of the gas chromatograph and inside the sample line was another PID. Next slide. During this monitoring deployment, a significant benzene emission was observed during the 1-hour sampling period. At the peaks on the left near the 4 p.m. timestamp, you can see a short duration of the emission for about 10 minutes. The mobile lab's PID sensor correlated with the SPOD detections. It can be seen in that same graph with the other two peaks. The gas chromatograph signal at the top with the green line also showed a correlation with the PID sensors, but the concentration is averaged over a 1-hour period, and this is why the green line is flat and horizontal. Next slide. And here we have accessories that come along with the SPOD. It includes the AC power adapter, the USB configuration cable, which connects the laptop or your tablet to the instrument. Optional accessories are the solar panel for remote locations, the tripod, an anemometer, an outdoor power supply, the canister valve controller, and the particulate matter sensor. We do not offer the sampling canister, but we do offer the pressure regulator assembly and an actuator valve, which are not listed on the slide. Next. So in summary, the SPOD in conjunction with the anemometer can distinguish on-site and off-site emissions. It can identify leak location. It can identify real-time emissions using the Sensent Connect web platform. The SPOD can provide support for site-specific monitoring plans, and it can trigger remote collection of air samples for laboratory analysis. Thank you.
All right, thank you so much, Ms. Espy. Definitely learned a lot from that, and I really like the concept of real-time alerts, something our community partners have been really excited about. And of course, we'll take additional questions from the comment section at the end. But now we'll shift gears to our academics. And first up is Dr. Susan Enenberg. So I'm just going to go ahead and share your presentation.
Great, thank you so much. Really appreciate the invitation to speak here today, to be a part of this very interesting panel of many different types of new technologies that we can deploy to track and address air pollution injustice. And I'll be talking today more specifically about using satellite data, and then Dr. Pusede, who will follow me, will go into more detail on some really groundbreaking work that she and her group have done to examine air pollution injustice and applications of satellite data. So next slide, please. There's a long history of air pollution and justice research, and more recently, in the past 5-10 years, we've been able to use big data to address the problem. So just a couple examples of how big data have been used. On the left-hand side here is we have a study by Colmer et al. That was published in Science in 2020 that showed that although PM 2.5 levels have dropped overall across the United States, those areas that were most and least polluted in 1981 remain so today. And that's despite the dramatic decline in air pollution levels across the United States in response to our highly successful Clean Air Act and the regulations that go along with it. So while we have brought down regional air pollution, the areas that were most polluted in 1981 remain the most polluted areas today. And on the right-hand side here, this is a study by Chris Tessum and colleagues that was published in the Proceedings of the National Academy of Sciences in 2019. And they used a modeling approach to show that there's a large difference between the environmental health damage caused by a racial ethnic group and the damage that group experiences. So if you just take a look at the two bars on the left-hand side here, this is for the Black population. We have the PM 2.5 exposure that this group causes versus is exposed to. And we see much higher level of PM 2.5 that this group is exposed to versus cause. For the Hispanic population, we see a similar pattern, and then the opposite pattern for the white population on the right-hand side here, where we have a higher PM 2.5 level that is caused by this population compared to the PM 2.5 level that this population is exposed to. And because they were able to use a modeling approach, they were able to break down this this pattern into the sources of pollution, both in terms of the types of fuels that are combusted and the end uses that those are used within. Next slide, please. When I say that we're using big data now, we can use big data to study air pollution and justice. What do I mean by big data? There's a lot of different types of data that we could use to address this problem. We've heard a lot about ground-based monitors and sensor networks already, so I won't go too far into that, but I'm really energized and excited about this new market of sensors that we have, where that really dramatically lowers the cost of ground monitoring of air pollution compared with the federal reference monitors that you see pictured on the left-hand side here. And that's a real opportunity. We can also use models, both statistical models and physical models. These physical models divide the world into pixels, and they use our best understanding of the chemistry and physics that govern atmospheric transport and fate and chemistry. And we whittle that down into a series of hundreds of equations, and typically are using a supercomputer to solve for these equations in all these grid cells, all these pixels around the world, and estimate pollution levels everywhere on the planet, even in places where there are no monitors. Statistical models do something similar, but those are typically not capturing the processes, the physical and chemistry processes that are leading to those differences in pollution levels within each pixel. Both of these types of models can be very, very useful, both statistical models and physical models. They are estimates. So these are not observations, these are estimates. And then on the right-hand side here is what I'll be talking about most today, which is satellite remote sensing. We now have an extensive fleet of satellites that are orbiting the planet and taking snapshots of the composition of the Earth's air, mostly one time per day now, but we're launching new satellites, and one just launched earlier this year called Tempo that is geostationary. It's fixated over the United States as the world spins. It will continue to take snapshots of the atmospheric composition of the air in the United States on an hourly basis throughout all daylight hours of the day. Next slide, please. What are the advantages and disadvantages of using satellites to measure air quality? I know this is a relatively new application for satellites and a relatively new tool to study air quality injustice. So some of the advantages are that we have estimates everywhere around the planet where there are no clouds and reflective surfaces. So right now, these satellites are not capable of taking measurements when there's clouds and reflective surfaces. So we have to sort of work around that. Another advantage is that we can achieve complete geospatial coverage, especially if we combine satellite data with other information in a model. So those 4 types of data sources that I talked about on the last slide are not mutually exclusive. We can actually integrate data, integrate information from multiple sources, and get to more accurate information that leverages the strengths of each type of exposure assessment technique. Satellite data are capable of going to increasingly high spatial resolutions, all the way down to 1 kilometer or even finer. And that's enough now to be able to differentiate neighborhood scale pollution levels. We still can't get to the street level, but we can get to the neighborhood scale. And I'll talk about that in more detail in a moment. And then for some pollutants, a good example is nitrogen dioxide. There's a very high correlation between the satellite estimates and the ground monitors. So even though the satellite is observing a column of air, the amount of molecules in the column of air between the Earth's surface and the satellite, which is not what we're breathing necessarily here at the ground, there's a high correlation between what the satellite sees and what's happening at the ground for particulate pollutants and nitrogen dioxide especially. So there are many really important advantages of using satellites to measure air quality, but there's also disadvantages. We can't observe all chemical components in the atmosphere, and we can't monitor surface concentrations or nose level pollution that we breathe. Satellites, again, monitor molecules in a column of air between the Earth's surface and the satellite, and that there is a high correlation for some pollutants between what the satellite is observing and what's happening at the ground, but that's not necessarily true for all pollutants. We often have to combine satellite data with other information to produce health relevant estimates, and that can be quite data intensive. So this is still a data intensive process to use satellite data to track air quality. Like I said, currently satellites are mostly polar orbiting. That means they're orbiting around the planet, and they're taking about 1 snapshot per day over every location, typically in the early afternoon, about 1:30 p.m. But new missions are geostationary, and they're able to capture full daytime coverage over one particular region of the Earth, like the United States. Next slide, please. So which air pollutants are measurable from satellites? Some of you may be familiar with satellite-based estimates of fine particulate matter, or PM 2.5. And those are not observations of PM 2.5 directly from the satellite. Those are typically taking satellite observations of something called aerosol optical depth or fire detection. Satellites can detect where fires are occurring and use those to infer nose level PM 2.5 when we combine those measurements of aerosol optical depth or fire detection with atmospheric models. So those are getting pretty good. Ozone, as you may know, is at the ground level is associated with respiratory effects and also premature mortality. There's currently no information from satellites on nose level concentrations of ozone because the amount of stratospheric ozone, the amount of ozone in the stratosphere is so high that it obscures any signal of ground level ozone. Nitrogen dioxide, or NO2, is probably the most straightforward pollutant to observe, and it's also an excellent tracer of fossil fuel combustion. Anytime we're burning fossil fuels, we're releasing NO2, and therefore it's a really great tracer of where fossil fuel combustion is occurring, really in any type of combustion process. Could be industry, energy generation, transportation, et cetera. So I'm going to focus on NO2 in several of the upcoming slides. Carbon monoxide is another tracer of combustion. We typically don't worry too much about carbon monoxide in the ambient atmosphere. We do worry about it in the indoor settings. And then there's a range of additional pollutants: sulfur dioxide or SO2, ammonia, formaldehyde, and also surface ultraviolet radiation, where the precision and accuracy are not currently suitable for most health studies, but again, we're improving in these areas as well. Next slide, please. So I want to just walk through one case study that my group led, focused on health and air pollution disparities in Washington, D.C., which we did in partnership with the D.C. Department of Energy and Environment and also the D.C. Office of Health Equity. The Office of Health Equity had just released the DC Health Equity Report in 2018, and you're seeing one image of that from that report in the left-hand side here. This diamond is the District of Columbia, And the underlying green color shows the pediatric asthma emergency department visit rate per 10,000 people. And the red dots show life expectancy. There's about a 20-year life expectancy differential between some neighborhoods in the southeast quadrant of Washington, D.C., and other neighborhoods in the northwest quadrant of Washington, D.C. And we have similar disparities shown in that green color for pediatric asthma emergency department visits. For those of you familiar with Washington, D.C., this also looks like the map of racial segregation, somewhat unsurprisingly, where the eastern half of the city is majority Black and the western half of the city is majority white. So we wondered, how much is air pollution injustice contributing to this 20-year life expectancy differential and the differential rates of asthma as well? What data sources could we use to explore this question? Well, on the right-hand side here, we have a map of the federal reference monitors in Washington, D.C. That are measuring PM 2.5, and there are 5 of them. It looks like 4, but 2 are co-located. And this is too sparse for us to really get at neighborhood scale differences in pollution levels. Next slide, please. What we can do with satellite data, which is shown on the left-hand side here, this colored map that goes from blue to red, we're able to attain this full geographical coverage, full geospatial coverage. So we can get satellite-derived PM 2.5 concentrations with a continuous spatial surface of exposure estimates. And this was a study led by Maria Castillo. And what we were able to use this spatial distribution of PM 2.5 with full geospatial coverage and estimate PM 2.5 attributable premature mortality rates. And that's what you're seeing in the Earth Observatory map on the right-hand side here. So we have areas in the eastern half of the city have both the highest rates of PM 2.5 mortality and the highest percent Black in the population. And the opposite is true in the western half of the city. We have the lowest rates of PM 2.5 mortality and the lowest rates of percent Black. And so this was a study that we published in the journal GeoHealth back in 2021, and then NASA created a much better looking, although very concerning, image that they posted on the Earth Observatory in November 2021. And this actually traveled much farther in terms of public engagement than, of course, our scientific study that was published in the journal GeoHealth did. Next slide, please. So that's for PM 2.5, but PM 2.5 is actually, as you saw in the image I just showed on the last slide, it doesn't actually differ that much within individual cities because it has so many sources and it lives for days to weeks in the atmosphere. Much of the disparity that we saw was actually driven by the disparity in the underlying disease rates and not in the pollution levels itself. One pollutant that does vary quite a bit more spatially within individual cities is nitrogen dioxide. And as I mentioned, we can measure nitrogen dioxide more directly from satellites than we can using for PM 2.5. NO2 is a precursor to PM 2.5 in ozone. That means it reacts with other chemical components to create PM 2.5 in ozone. And it's a marker for traffic-related air pollution. It's also itself associated with respiratory effects, cardiovascular effects, and mortality as part of that overall traffic-related air pollution mixture. As I mentioned, compared with total PM 2.5 mass, NO2 has sharper gradients near emission sources. So when we're interested in environmental injustice and what impact nearby sources have on the surrounding population, NO2 is a pollutant of interest. It has a shorter atmospheric lifetime, hours compared with days, and has less influence from regional pollution sources like agriculture and wildfire smoke and dust that contribute a lot to PM 2.5 in urban areas. NO2 is also a surrogate for urban combustion-related air pollution, including PM 2.5 components that have more spatial variation, like black carbon and particle-bound polycyclic aromatic hydrocarbons that I know a lot of communities that are surrounding polluting facilities care a lot about. And as I mentioned, satellite NO2 column observations are tightly correlated with NO2 observed at ground monitors. Next slide, please. This is what an image of a temporally averaged NO2 looks like from satellite data. So this is NO2 from the TROPOME sensor on the Sentinel-5P satellite from the European Space Agency, average for all of 2019 in the middle for the entire globe. And then just on the right-hand side here, this is for the Washington-Baltimore region. So you can really start to pull out urban areas. You can start to pull out individual facilities and highways. If you just look at the highway that connects Washington, D.C. and Baltimore, you see higher levels of NO2 on that highway compared to the surrounding area. This is really unprecedented information that we have with, again, full geospatial coverage. And these images were created by Dan Goldberg from George Washington University. Next slide, please. So what can we do with this type of NO2 information? Well, this is a project led by Dr. Gage Kerr from George Washington University. And he looked at how much did the transportation, the passenger vehicle traffic change that we had during the pandemic, how much did that influence NO2 disparities across the country? So if you just look at the top row here for all census tracts, NO2 concentrations in the least white census tracts across the United States were double those in the most white census tracts across the United States in 2019 prior to the pandemic. During the 2020 lockdowns, we saw that both the orange dots and the blue dots shifted to the left, indicating that NO2 dropped for both the least white census tracts and the most white census tracts. But we saw something really concerning, that the NO2 concentrations during the 2020 lockdowns for the least white census tracts were still about 50% higher than the concentrations in the most white census tracts prior to the pandemic. So what that indicates is that NO2 disparities were so large prior to the pandemic that even about a 50% drop in passenger vehicle traffic was not enough to eliminate those disparities. And we saw that pattern hold for all urban tracts across the United States and these major urban areas as well. We found that the proximity of highways and diesel traffic in minoritized communities were a key driver of these NO2 disparities. Next slide, please. Now, we wanted to take this further and combine the information about exposure with information about vulnerability. So not just how much pollution are people exposed to, but what is the impact that pollution is having on their health? And so Gage then looked at PM 2.5 attributable premature deaths per 100,000 people, which is on the left-hand side here, and NO2 attributable pediatric asthma cases per 100,000 on the right. And we see a few things. One is that PM 2.5 attributable premature death rates are going down over time, and that's aligned with how PM 2.5 is dropping across the United States. But despite that decline in PM 2.5 attributable premature deaths, we still have this consistent disparity, this persistent disparity with higher rates in the least white census tracts compared with the most white census tracts. On the bottom line here, the line chart with the hollow circles, we see the ratio of those values, the PM 2.5 attributable premature deaths per 100,000 in the least white census tracts compared with the most white census tracts. And we see that ratio is about 1.32, indicating that the least white census tracts have PM 2.5 mortality rates that are about 30% higher than those in the most white census tracts. Now, if you shift to the right-hand side here for NO2 attributable pediatric asthma cases, we see much greater disparity. So even though NO2 is declining as PM 2.5 is, we still see this persistent disparity, and the disparity is much larger for NO2 attributable health burdens compared with PM 2.5 attributable health burdens. So we see much larger disparities for NO2 compared with PM 2.5. Next slide. Now, I'm really excited. If you could click one more time, see if the last figure shows up here. Nope. Okay, go back one. I'm really excited about new satellite missions, TEMPO and GeoXO, or geostationary satellites. There was a picture of TEMPO here that got dropped off, so sorry about that. But the figure on the left shows the spatial footprint of TEMPO compared with the previous legacy satellites that were measuring NO2, OMI and GOM2, and you can see TEMPO is quite a bit higher resolution. This is over the Washington, D.C. area. So TEMPO is already flying. We just saw first light images, and we should get data from TEMPO early next year. So I'm really excited about this. We'll have hourly satellite-based observations of NO2 throughout the daytime over the United States. And then NOAA, the National Oceanic and Atmospheric Administration, is developing the next generation satellite, GeoXO, to launch in the early 2030s. And it's really a really important mission to continue our atmospheric composition data source, our space-based atmospheric composition data source. And this is also intended to be geostationary and taking hourly snapshots over the United States. Next slide, please. So I just want to end with two more slides. One is how satellite data can be used in environmental justice applications. And really, I've listed here some thoughts from my head, but this is really just scratching the surface. And I think, what would be great is if people started to think about, with the questions and applications that they had top of mind for their work, how can satellite data be useful to those applications? So just things like improving information and environmental justice mapping tools, identifying disadvantaged communities, characterizing disproportionate environmental burdens and associated health risks, discovering associations between environmental health risk factors and health outcomes, understanding contributions of different emission sectors and sources to environmental injustice. And I think Dr. Puseda will talk a little bit more about this in the coming talk. Identify and address local polluting sources. We can track air pollution from emerging industries, oil and gas development, and transportation related to warehousing and goods movement. This is an eye in the sky pollution tracking technique that these satellites are flying, and we can make use of the data to track the impact of industries that are emerging in new locations. Next slide. I would invite everyone to participate in free online training that is now available from NASA. It's NASA's Applied Sciences training. There is a QR code. It looks like some words are over it, so hopefully you can still use it. But you can go to this website regardless and sign up for the satellite data for air quality training. It's free. It's openly available now. I've listed some of the people who participate as trainers. And there's also an online community of practice message boards. If you go to haq.community.forum, you can communicate with other people that are interested in using satellite data for air pollution injustice, not even just air pollution injustice, but all environmental injustice, share tips and tricks and questions, and really just start to build this community of practice. So thank you very much. I look forward to the discussion.
All right, thank you, Dr. Edinburgh. And it's really, really fascinating to see the future of geostationary monitoring, like you mentioned. And of course, I really encourage those on the stream to look at those training resources to be involved. So thank you so much. And we will finish up with our final speaker, Dr. Puseda. I will pull up your presentation.
All right. Well, thank you. Thank you for inviting me and giving me the opportunity to speak. I'm excited to share work from my lab related to the application of satellite NO2 data to study in NO2 environmental inequality issues. Before I begin, I wanted to acknowledge the students in my lab who have done the work that I'm going to share with you today and who also have contributed to this line of research in our lab more generally. And we do this very collaboratively, and I've listed the many collaborators that we have here as well. Next slide. So I'm going to focus on one specific pollutant, that's nitrogen dioxide, that Susan covered very well. This comes from a satellite called Tropomi, and you're looking at that map across the United States. Nitrogen dioxide is emitted by vehicles and power plants. It's a proxy for toxic combustion pollutant generally, and it's chemically reactive, and it goes on to form ozone and particulate pollution, and it's visible from space, and we can see here major cities and power plants across the U.S. Next slide. So a lot of our work has focused on doing detailed evaluations of these observations for this application. And we've come to sort of identify two needs. First, that we have to have satellite measurements that resolve neighborhood level differences. This isn't just for NO2, but can be thought of broadly. And the second, as Susan mentioned, the satellite is out in space and it's looking down to the surface. And so we're seeing pollution in that full column of air. And for our work, we don't need to know the surface concentration, but we do need to know that the patterns we see in the columns reflect those patterns at the surface. And so really, we've taken the approach of using a wide variety of data, in particular measurements collected on aircraft, in order to demonstrate this, at least for Tropomi. Next slide. And I want to highlight again some of the assets of these observations. Certainly they support research, they support decision making. They also support a political accountability and community monitoring. And that's a point that I'll return to in the end. And these observations, they're spatially comprehensive. Their spatial resolution improves with temporal averaging. That's a piece that I'll talk about a little bit later on. And really, the temporal information we get from satellites can be really useful for source identification. And so in terms of describing inequality in this talk today, I'm going to focus on identifying the specific sources of pollution that drive it. Next slide. So here we are again looking at NO2 across the United States. And about a third to in some cases more NO2 pollution comes from heavy-duty diesel trucks. And heavy-duty diesel trucks also emit a lot of other toxic pollutants. So this map here that I'm showing you, this is an image on average just on weekdays. Next slide. And here I'm showing you that same map on weekends. So if you could just toggle back and forth a couple of times. We have here a really powerful observational constraint on the amount of NO2 pollution that comes from diesel trucks. So it turns out we drive our personal vehicles about the same amount weekends to weekdays, but we see a dramatic decrease in the amount of diesel truck emissions. So we're going to use this observation as an experiment to identify the contribution of diesel truck emissions to NO2 inequality at the neighborhood scale. So next slide. So in order to answer in order to know the contribution of diesel trucks, we have to know the change in emissions weekday to weekend. We have to know the fraction of vehicles that are parked. And so weekday to weekend, we find that about 60% of these vehicles are parked, and we see a reduction of 60%. And so it's not enough in our case to just know how the emissions change, because the concentration is affected by the winds and also the lifetime of pollutants in the atmosphere. But this is the experiment itself, a 60% reduction in diesel traffic. Next slide. And so here I'm showing you the results. We looked at 52 cities across the United States, and we calculate the population weighted NO2 column at the census tract scale, and we use that to look at inequality by race, ethnicity, and income. And so each one of these circles in this figure is a city, and we're looking at the weekday NO2 inequality on the x-axis, in the summertime in gray, in the winter in blue, and on the y-axis, we're looking at the inequality in those same cities on weekends. And so one thing we can see in the observations is that the relationship is very tight in the summer. That's because the lifetime of this pollutant is short, so we see a strong correlation between emissions and concentrations. But we can infer from the slope the effect of that large change in diesel emissions. And so what we conclude is that a 60% reduction in diesel NOx emissions would cause a 40% reduction in NO2 inequalities with race, ethnicity, and income across the United States. On average in these 52 cities, certainly there's regional variability. And this allows us to get at testing very specific policies. And this recent rule by the Biden administration was actually to reduce diesel NOx emissions by 60% by 2045. So in effect, we have tested that outcome. It's not, it would have a large effect, but we can see here that it doesn't eliminate inequalities. Next slide. So from this point, we became really curious about, well, how can we get more information from the temporal component of the observations as opposed to just the spatial? And so a lot of work using satellite observations has relied on heavy time averaging. And this is because we can increase the spatial resolution if we time average. So we took it in the other direction. We said, all right, well, let's use the individual daily observations. At best, the satellite resolution for an individual day is 3.5 by 5.5 kilometers. So it's much coarser. It's certainly much coarser than an NO2 distance decay gradient away from a source, for example. But we did a lot of evaluation with aircraft observations to show that we were still capturing about 80% of inequalities at the census tract scale. But what we gain from doing this is a lot of information in time that we can use to understand the effects of specific policies. So we're going to zoom in here to New York City, and I have the NO2 inequality on the y-axis. This is specific for Hispanics and Latinos. And I've plotted it on the x as a function of the overall pollution in New York City. And we can see a really strong relationship. The more pollution in a city, in New York, in other cities we see this, the more inequality we have. But this is the absolute difference in concentration between groups. If you go to the next slide. Here I've plotted the relative differences between groups, or the percent inequality. And you can see now that there's really no relationship between inequality and overall pollution. And so from this, we can learn about policies that really, if we don't actually change the location of where sources are, then we're not developing policies that address inequalities. And so what we get from this is an observational evidence that targeted rather than sector-based approaches are required to eliminate inequalities. We also have observations that are useful for accountability as to whether promises in recent legislation in New York and New Jersey around the sort of reducing the cumulative burden of sources in overburdened communities are met. Next slide. And I'm going to show you one more example of work we've done with a satellite that speaks directly to policies. In this case, we're going to go to Houston, Texas. And so I want to bring it back to an air pollutant. This is ozone. This is regulated under the Clean Air Act. Cities spend a lot of time trying to reduce ozone, including in Houston, which is ranked among the top 10 worst ozone polluted cities in the United States. And ozone can be difficult to control because it varies nonlinear with its precursors. So on the y-axis here, we're looking at the ozone production rate. And in the x-axis, we're looking at the total amount of NO2. And NO2, as I said before, is a precursor for the amount of ozone. And so if we're on the left-hand side of this at low NO2, additional reductions in NOx emissions are going to be very effective. But as we move to higher NO2, we see here that actually there'll be a NOx disbenefit to reducing NOx further, although ultimately it's going to have to be done. But here, VOC control is effective. All right, so this is what a regulator is thinking when they develop their ozone air quality policies, and this is called an ozone isopleth. If you go to the next slide. So what we've done here is taken the Trobomi NO2 inequalities and put them on the x-axis in place of the overall amount of NO2. And on the y, we're showing you a sort of an empirical model for the amount of ozone. And what's important here is that we've reproduced these ozone isopleths no longer as a function of the amount of NO2, but here as a function of the inequality in the distribution of NO2. Next slide. So we know that locally targeted NOx reductions are required to reduce NO2 inequalities. These sector-based approaches just won't do it. But what we see here is a coupling between citywide air pollution issues and how sources are distributed throughout cities. And so we conclude that permitting and policies consolidating sources in a subset of neighborhoods affect ozone. And that decision-making that has clustered ozone precursor emissions, in this case in the Houston Ship Channel, is going to maintain high ozone. And what I would say to a policymaker here in Houston is that Houston is not going to come into compliance with ozone air quality regulations until it addresses the inequality in the distribution of primary pollutants. Next slide. So to conclude, I just want to come back to this notion of the observational strengths of satellites. They support research, they support decision-making, political accountability, community monitoring, but really here what satellites are doing are providing material evidence of local knowledge around air pollution, in particular in places without surface monitoring, where emissions are poorly known, and where relationships between emissions and concentrations are complex and nonlinear. And as satellite records develop, there are going to be real opportunities to hold decision makers accountable, particularly for the large number of environmental justice related promises that are taking place right now. Next slide. And so just in terms of community monitoring specifically, we have detailed satellite measurements that are spatially comprehensive. The data come with no maintenance burdens to the user, which I think is a great asset, as long as these barriers to their use can be brought down. And I will say also, as we go forward, we do require a deeper understanding of the limitations of some of these data sets as well as their assets. And this links back to something that Evan was talking about, sort of that there is no perfect sensor, that really we don't, and I don't think we need that, right? But what we do need is a careful and detailed understanding of the uncertainties and limitations of the data that we are using. And so with that, I thank you for your time.
All right, thank you so much. I think it's really great that you provide recommendations to policymakers as well. That really gets into this idea that Dr. Wilson mentions of actions-oriented solution science. So thank you so much for that. I'm looking at the chat box. I don't see any questions from the audience, but now is the time to ask away. But before that, I did have one question for Ms. Espy. So when monitoring VOCs specifically, they aren't regulated by the EPA under the Clean Air Act. So how could you explain how your products could support regulatory efforts? I'll kind of start off the Q&A with that.
Well, the SPON itself is, it doesn't give a measurement. It would have to be, you'd have to take the samples and submit them through a GC to get your results. In other words, the SPOT itself could not do that for you.
And then Dr. Cross, I had one question for you, still letting the audience members ask away. How have you seen low-cost real-time air monitors evolve over the years? Because you've definitely been in the field for several years. So what are some of the main takeaways you've seen over the last, let's say, decade or so since you became involved?
Sure. I mean, to some extent, they haven't. Everybody deploys a plant tower sensor, and we've just learned how to leverage that measurement better, more accurately, and understand some of its limits. But, so I think it's on the hardware side, there haven't been a lot of innovations. I think connectivity has improved, and that opens up, more and more opportunity to sort of lower the barrier to entry of managing large networks. You don't need an IT team to do this. And in some cases, from a community perspective, you can outpace the regulators pretty quickly on monitoring. So that's exciting, but we're still in this really sticky gray area of trying to reconcile the data quality objective and align on an air pollution question. And I really appreciate the two talks that talked about the value of NO2 as a proxy for essentially UFPs and black carbon, which are much, much more important for environmental justice applications at fine scale, but for which there are no direct scaled measurements currently.
Thanks for that answer, Dr. Cross. Dr. Edinburgh, I see we have a question from the chat, so I'm just going to go ahead and boost that to the session. So the question is, what are some of the health-related data sets that are currently being used for these evaluations? So how are you integrating health, I'm assuming, into these air quality measurements?
Yeah, I can take a first stab at that. It's really a great question because I think many of us in this air quality community spend a lot of time talking about improving air quality measurements and air quality data availability. And we don't talk as much about the availability of health data and high resolution health data that can capture this dual impact that communities are experiencing of both pollution exposure and underlying disease that is inequitably distributed. And there really isn't a great solution right now in terms of health data. So we can get health data from our local health departments. It does take a while to do that. You have to make a specific request. The data are often suppressed for privacy, to protect privacy. If you get to a high enough spatial resolution where you don't have enough cases, those data will come suppressed. And often you have to go through an institutional review board to ensure that you're using the data appropriately and within ethics. So it does, there is a barrier to using administrative health data. Not criticizing the barriers, they're for good reason, but it does make it a little bit more complex to use. To use. There are other data sources that have broader geographical scope and sometimes are estimated. The value of estimated data are that you don't need to suppress the values to protect privacy. So we're increasingly getting information from the CDC and other sources that are estimated for small spaces, small localities. And so often we use that for estimating the health burdens associated with pollution on the neighborhood scale.
Thanks, Dr. Edinburgh. Would others like to chime in? We have about 5 minutes until we have to end the session. So I'll extend this to the rest of the panelists, and then we can conclude if there are any more questions in the chat.
I mean, I actually think there was a conversation I had the other day with a regulator who likes to think of local air quality monitoring as public health protection, and she distinguishes that from regulatory monitoring and regional monitoring. And I think that's where, I think if we all start to form a narrative around the public health protection piece of local monitoring, whether it's from satellite drive products or surface measurements, using that public health protection like tagline could actually be quite effective, because we're often in a gray area from a regulatory perspective, strictly speaking.
All right, we do have one additional question. This one's for Dr. Annenberg. Seems like you're very popular today, Dr. Annenberg. Is it meaningful to use the NO2 census data for a small township or municipality to compare air quality and health changes over time?
Oh, this is a great question. Thank you for this. And I don't want to put Dr. Pissette on the spot, but I think she'd also have really great insights about the uncertainty of the data products when it comes to smaller townships and cities compared with the major urban areas that I showed in some of my results. But that is one value of the satellite data, is that we're starting to get a long enough record of data that we can look at trends over time. And within some, will always be uncertainty, but it is an observational approach to observing how pollution is changing over time, regardless of where you are and whether there's a monitor there. So I do think that, we can get into, you ask multiple scientists this question, I'm sure you can sit here for hours talking about all the various complexities of a case like this. But when it comes down to it, I think that's what satellite data offer, is that you're able to make observations in places where there are no monitors and look at trends over time.
Thank you, Dr. Annenberg, for that. So I don't see any additional questions, or did other panelists want to jump in?
I might just add that, that the census unit is often used, but it doesn't have to be. We could, especially with geospatial data, think of a lot of other community relevant units as well. School districts define neighborhoods in different ways, for example.
Awesome. Well, I wanted to, again, just thank all of you for being here today, for speaking and presenting. I want to thank our audience members, and I look forward to seeing you all during the third concurrent sessions, which will begin in about 15 minutes. So again, thank you all, and I hope to see you soon.